Alright, so today we're going to look at section 7.3, which is on solving mostly trig equations. We'll do a little bit with inequalities, but solving them graphically. We're going to do these same kind of problems again in section 7.6, okay, next week. But we're going to solve them algebraically. Okay. What's nice about graphically is we don't have to worry as much about formulas, like learning the algebra part, and we can solve problems graphically that you can't do algebraically. Like there are some algebraic trig equations that people could make up, and I wouldn't know how to solve it because it's too complicated. Well, graphing, nothing is too complicated. You just put something in y1, you put something in y2, you just see where they cross. The downside to graphing is sometimes you can't always get an exact answer if the calculator gives you a decimal where they cross. Now, one thing we have to remember here is how many solutions there are to a trig equation. If you can find at least one solution, and you could zoom out forever, how many solutions would you see? If you can find an answer, let's say you could find one answer in the first cycle. Yeah?
You'd find infinite solutions.
Right, you'd find not only one answer in the first cycle, but one answer in every single cycle. So there would be infinite solutions. So when we're solving problems, if the directions say find all solutions, that's where you have to put plus the period times n on the end of the problem. And I'm pretty sure every question today is going to say all. Okay. So the first step is to find all the solutions that are within one period. And we're going to do that by setting the window on the graphing calculator to one cycle wide. And then we're going to take into account the fact that, well, there's one solution in this cycle, but it really repeats forever. So to indicate that it repeats forever, you have to know the period. And that tells me how often it repeats. So the answers that we write are going to look like the solution, which you get from doing the intersect, but then you have to put plus the period times n. And you have to write something that looks just like that for every single solution. So if you see 2 in a cycle, then you're going to have to do 2 intersects. If you have 6 answers in a cycle, then you got to do 6 intersects. You have to do it as many times as answers. So since the period is going to be important, we're going to talk a little bit about the formulas again to find the periods, the 2 pi over b and pi over b. Okay, I know we've already talked about them, but we've never talked about having a problem where you have a trig function raised to a power. So what does raising it to a power do to the period? It affects it. Okay? So we'll make a table that explains what happens. Okay, any questions on that? So we're going to start out with one that would have been like on the homework last night. Okay, a very simple trig equation with no exponents at all. Just sine of x equals 0.8. Now, if you're thinking, yeah, I could just solve this with algebra. I don't really need to graph it. You're right. You could take the inverse sine of each side, and that would cancel out the regular sign, and you'd have the answer. So if I was doing this problem algebraically, I would just do inverse sine of 0.8. Well, let's keep that number in mind, and let's graph it, and let's see if that's what we got, because graphing is what we're focusing on today. All right, so if I want to graph that, what would I put in y1? Yep.
Sine of x.
Okay, put in sine of x. And what would I put in y2? Yep, 0.8. And remember, you need to find all the solutions within one cycle. One period. What's the period of the sine function? Yeah, 2 pi. So what's the easiest way that I can set a window on my calculator that's 2 pi units wide? Technically, the window I have up there right now is 2 pi units wide, so I could use it, but I don't want to. Yep.
0 to 2 pi.
Let's go 0 to 2 pi. And when you graph sine, what's the highest and lowest that it goes? Yep.
Negative 1
-1
to 1.
to 1, so -4 to 4. That's fine. I mean, I wouldn't do like -50 to 50. That's going to be too big. But -4 to 4 is fine. Okay, let's hit graph. Okay, there's my sine function. There's my line at 0.8. And how many answers does it look like I'm going to get per cycle? Yep, 2. Right? Let's find the first one. Well, we already know what it should be, but let's check. Second, calc, intersect, and I get 0.927. That's exactly the answer that I got a lot faster just by doing inverse sine. The problem is there's a second answer, and the calculator did not give me the second answer. It only gave me one. It'll never give you the second answer when you solve it like I did. It'll only give you the second answer if you're graphing. So we got 0.927. And the other answer, well, I know how to get the other answer based off that 0.927. Okay, the other answer is going to be pi minus the answer that I just had. It's going to be 2.21. Let's calculate the intersect and see if that's what we get. So let's go here. Calculate the intersect, and it is 2.21. So even though the calculator only gives me one answer, there is a way to get the second answer from the first answer without using a graph. The way that I use to subtract this number from pi, that's something I'm going to teach you in 7.6. For now, we're going to do it graphingly, or using the graphing calculator. Okay, so 2.21. Now, if that's all you put, you haven't answered this question. You have found 2 solutions to this problem, but I want to know all of them. So what do we have to put on the end of each one of these to indicate like that this answer is going to occur again, right about there? Yep.
You have to put plus 2 pi in.
Right. And n represents the number of cycles later you want to find the answer. So if you want to know what's the answer 23 cycles from now, take 2 pi times 23, add it to that number, and you will get the answer 23 cycles later. And same thing on this one. If this was a degree problem, well, it didn't say whether to do it in degrees or radians, so I chose radians. But if it said to do it in degrees, well, the first thing you'd have to do is put your calculator in degrees. And you wouldn't want to set your window 0 to 2 pi. 2 pi is radians. What's 2 pi the same as in degrees? Yeah.
That's 360.
360. So if I wanted to do this in degrees, I could. But you need to set this to 360, and then this would also be 360 instead of 2 pi. All right, but we'll stick with the radians for now.
Your window for that graph, was it 0.8 your x min or your x max?
Neither. That was my y2.
Oh.
Yep. So 0.8 was my y2. It's the red line. Any other questions about how we set that one up or how we solve it? So do I think graphing is a good approach on this one? No, not really. I can do it a lot faster just by taking inverse sine. But let's stick with the graphing for now. Okay, so sometimes we're going to solve problems where they are equal to 0. Does anybody remember what you call it when you're solving for an answer that when you plug it in gives you 0? That number is called that's called the root. So when you set something equal to 0 and solve it, you're solving for the root. You can also call it the 0. So like something like this. If I was solving that in Algebra 1, if I wanted to know the root, well, you bring everything to one side. So minus the 10. And then you find out what number you could plug in for x to give you 0. In that case, the root would be 3. We're going to be solving for roots of trig functions. When trig functions are involved, there's usually more than one answer. Sometimes there's one, but there's usually more than one, especially if we consider that it goes on forever. So when I say more than one answer, I mean usually more than one answer per cycle. So what we're going to have to take a look at is what I mentioned earlier about what if you have like sine squared? Well, we know the period of sine is 2 pi. But what about sine squared? What about sine cubed? How does changing the power change the period? The other thing we're going to have to look at is, in this last problem, you had a single trig function, right? It was just sine. But what if you have a problem with more than one trig function, like cosine squared and sine? Both of these have different periods. Well, to find the period of this entire thing, it starts by finding the period of each trig thing. Okay, that's how we have to start. So we have to look at each term that has trig and find the period of those first. Then I'll show you how you find the period of the whole problem. So if you have a trig equation that has more than one trig term in it, the first thing is to find the period of each periodic term. Periodic means trig. If you have a term in your equation that's a number, let me go back to that problem for a second. Like this. 1 doesn't have a period. 1 is not a trig term. It's a constant. So you don't have to worry about finding the period of the 1. Just the trig terms. Once you know the period of each individual term, then you have to find the least common multiple. The LCM is the answer for the period of the entire problem. So like, let's say you were doing a problem and one of your trig terms had a period of pi. Okay, that could be like a tangent or a cotangent. And let's say something else had a period of 2 pi. What are some multiples of pi? Yeah?
2 pi.
Yeah, so we could start with just 1 pi, 2 pi, what else? Yeah. 3 pi, 4 pi. These are multiples of pi. So when you take pi, you multiply by something. How about multiples of 2 pi? We'll start with the smallest one. I'm not including 0 because that won't help. So start with the first multiple, but not 0. Yep.
2 pi.
So 2 pi, and then the next one, 4 pi, 6 pi, 8 pi. Those are multiples of 2 pi. So if one of your terms had a period of pi, and the other one had a period of 2 pi, you need to find the least common multiple of 1 pi and 2 pi, which, based on that chart, what's the smallest multiple that they have in common? Yep.
2 pi.
2 pi. The least common multiple has to be, how can I say it? It has to be at least as big as the numbers as the individual periods. Like if I was looking for the least common multiple of 2 and 3, it can't be smaller than 2. It has to be at least 3 or bigger. So that's one thing we're going to have to do. Find the periods, and then find the least common multiple. But what if one of the terms is something squared? Or what if I did sine cubed? I mean, what would that do to the period? What are the two formulas that we use right now to find the periods? We either use this one or this one. Yep.
Pi over b and 2 pi over b.
Right. We either use pi over b or 2 pi over b. And that's going to be exactly what we have to do with this. It doesn't matter if you raise it to a power. You're still using those two formulas. You just have to know when to use which one. Okay, so here's a summary of the periods. If you have any type of tangent or cotangent problem, doesn't matter if you raise it to an even or an odd power, the formula that I'm about to give you is going to apply. Or if you have a sine, a cosine, a secant, or a cosecant to an even power. So any one of these 8 situations, 1, 2, 3, 4, 5, 6, 7, 8. The formula that you would use in those 8 situations is pi over b. Now, I don't think we're going to do any problems where b is negative, but if it was, you want to make b positive. Because remember, the period measures how long something is, and it doesn't make sense to say something has negative length. So these 8 situations are going to use the formula pi over b. Can somebody remind me, where do you look for the b? Like where would that be? Yep. Yeah, maybe I should fill that in just so if people want to see that. So b is what's in front of the x. And the other formula we're going to use, Jalen just said it, it's 2 pi over b. When do you use that one? Whenever it's not this. So the only thing we haven't looked at is sine to an odd, cosine to an odd, secant to an odd, or cosecant to an odd. Those are the other 4 cases. So I'll scroll down. For those 4, it's going to be 2 pi over b. And you would want the b to be positive because it's measuring a distance. And so for the test on Friday, it might be handy if you can't remember when to use 2 pi over b or when to use pi over b. I would write that down. If you can shorten everything I wrote somehow, you could try to shorten it. But that's when you use each one. And same thing here. B is what's in front of the x. So now to figure out the period of a trig function, you got to really take into account two things. What power is it raised to? That's going to tell you whether to use 2 pi over b or pi over b. And then, what's the b? So we got to look at both of those things. So now we're ready to look at this problem. So directions say find all the solutions. So first step, find the period of each periodic term. There's 3 terms in that problem on the left side. How many of them are periodic? Yeah. 2, just the trig ones. Cosine squared and sine. What's the formula that I use for finding the period of cosine to an even power?
Pi over b.
Pi over b. And what is b in this case? Yep, 1. It's what would be in front of t. There's nothing in front of t. So the period of this one is pi. This one is sine to an odd power. It doesn't have an exponent, so it's just sine to the first. So what's the period of regular sine? Yeah.
Pi over b.
Sine to an odd power, 2 pi over b, and what's b?
1.
1. So this one is 2 pi. So now we have the period of each periodic term. Find the least common multiple of the numbers that we just got. What's the least common multiple of pi and 2 pi? Yep. The least common multiple can't be smaller than either one of these. Like if I was finding the least common multiple of, say, 2 and 5, I couldn't say 3, because 3 is smaller than 5. It has to be bigger than the individual numbers. Yep.
Would it be 4 pi?
4 pi is a common multiple, but there's one that's smaller. Yep.
2 pi.
2 pi. 2 pi is divisible by pi, and 2 pi is divisible by 2 pi. So you have to find something that they both go into without remainder. Couldn't say pi here because 2 pi doesn't go into pi. That's like trying to divide 3 into 2. 2 is too small. For something to divide in evenly, it has to be at least as big as that number or higher. Okay, so that's going to be our period. That's very important because it tells me 2 things. 1, it tells me what to set the window on the calculator for. And 2, it tells me what to put on the end of each answer when I write all solutions. All right, so now how do we type that in? Well, when you see something like cosine squared t, this notation is not something you can put in on a calculator. This is a notation that you only see when people write it on paper. What this notation means is this. That's what it means. Cosine squared t means to take cosine and raise it to the second power. So why do people put the 2 in the middle? Because it's less writing on paper. If you want to put the 2 on the end, you can't do this, because that looks like the cosine of t squared. That's different than taking the cosine of t and then squaring it after. So they invented this notation for paper only, that if you put the 2 in the middle, then I don't need parentheses because it doesn't look like the t is squared, and it means this. Okay, so that's what that means. And to put it in, you're going to really just type it pretty much like I did on the right-hand side. So you're going to put in 2 cosine t. Well, I have to use x. And then just make sure that the exponent is on the outside of the parentheses. If you do it like this, you've now changed the order of operations. That's wrong. Now you're squaring the number you're plugging in before you take the cosine. If you do it like this, now you're squaring the number after you take the cosine. So 2 cosine squared x plus sine x plus 1. Anytime that the computer or the calculator opens a parenthesis for you, you need to close it at the appropriate spot. Okay. And then I don't really need to put anything in y2 because I'm going to calculate where it's equal to 0, and the calculator can do that automatically. So I don't need to put anything in y2. Unless you wanted to do this problem as an intersect, which I'm not going to. But you could. All right, so window. We need to set the window so that it is 1 period wide. What's the period of this one? Yep.
2 pi.
2 pi. I'm already set up. Most of them are going to be 2 pi today, just to kind of let you know. So let's just try it out. And there you go. So that's your graph. That is one cycle of this picture. Okay, looks a little more complicated than a wave because the formula is a little more complicated than just signing just a single sine or cosine. It's got some exponents in there. If you wanted to sketch what this is going to look like, you would take this section and you would copy and paste it. That's 2 cycles of the graph. So, how many answers does it look like we get per cycle? Remember, you're looking for where it equals 0. Yeah? Yep. It's just 1. You could zoom in here because if it did something like that when you zoom in, you'd want to check and see if it hits twice. But if you zoom in here, you will see that it just comes down, touches the axis, and bounces up. It doesn't go below. Okay, so that's the answer we need to find. So we're not going to do an intersect. What am I going to do? Yep.
You do 0.
I'm going to do a 0. And we're going to pick a value somewhere to the left. I'm going to go to the right, and then hit enter. And it tells me the answer is 4.71. Now, that is that. But that answer is going to occur again right there. How much later does that answer come back again? Yeah?
1 period.
1 period later, which in our case is how much later? 2 pi. And it's not just going to come back 1 period later, it's going to come back any number of periods later or earlier. But it's going to repeat forever. And that's the answer to that one. Yes?
What about the 1?
I didn't put in the +1?
Oh, I don't know.
Oh, if I didn't put in the +1, then it's all wrong. No, I put in the
Oh,
+1.
okay.
What are you doing? You're trying to scare me.
I forgot.
Yeah.
I was about to say, I typed mine in right, and I got the same answers.
So yeah, you gotta make sure you put in the whole thing. So we
Alright.
did. Any questions? Yeah.
Is it possible for something to happen like in 1 period and then happen 2 periods later? Or is it only possible for it to happen like every period?
Well, whatever happens in 1 period has to happen in every period. So it's very consistent. Whatever you see here has to happen exactly the same right there.
Okay.
And exactly the same before. Repeated forever. Okay, let's try this one. So I want to solve it like we did the last one. But what was the last one equal to that this one is not? Yeah?
It was equal to 0.
The last one was equal to 0, so let's get this one equal to 0. Doesn't matter if you put 0 on the left or the right. You can do it either way. Let's just say we put 0 on the left. What would be on the right if I put 0 on the left? Becca?
Would it be 3 cosine x minus tangent of x?
Yep, 3 cosine x minus tangent of x. Now, you're not ready to type this in yet. You've got to set your window. We don't even know the periods, so we gotta figure those out first. No exponents. So what's the period of the regular cosine function? Yep.
Pi over b.
Yep. And in this case, b is 1, so it's just 2 pi. And what about the period of tangent? Yep. Pi over b. Again, b is 1. So you've got the period of each individual term. What's the least common multiple of 2 pi and pi? Yep. It's going to be 2 pi. And now we're ready to set our window. Okay, set a window that's 1 cycle wide. In this case, I would go 0 to 2 pi. Now, up and down doesn't matter. It's going to go off the screen because it's tangent. Tangent goes up and down forever. So I would try -4 to 4. That's probably fine. Okay, so we've got that. We've got that. We just have to type it in. So 0 equals 3 cosine x. Probably better to just clear it all first. 3 cosine x minus tangent x. All right, let's graph that and see what we got. So as I said, it goes off the screen. And how many answers does it look like we get per cycle? In this case, yeah? 2. We're going to get 2. So this one looks a lot different than a wave. And if you take the pattern and repeat it, I don't know if it's actually all going to stay together because I'm lifting my pencil. I tried to do it fast enough. Yep, it did. Good. If you take that and repeat it, right there, that's what this graph looks like. That's the section that keeps repeating forever. All right, let's find our 2 answers. So second calc, 0. Okay, you can't do both at the same time, so you gotta pick one at a time. So your first one is 1.01. And the second one is second calc 0. I'm gonna pass it. I think I'm okay, just barely. 2.13. And what we have found is these 2 answers. And what do we put on the end of each one of them to indicate that it repeats forever? Yeah.
2 pi n.
Yeah, plus 2 pi.
Yeah.
There you go. So there's a problem that has 2 answers per cycle. Any questions on that one? Yeah.
Do you show the window again?
The window, yeah, it's the same window we used for the last problem, the 0 to 2 pi. All right, let's try this one. More just for plugging it in because there's a lot going on here. So you got some exponents we gotta deal with. So parentheses are going to be important. What's the period of, or what's the formula for the period of sine to an odd power? Yep.
2 pi over b.
2 pi over b.
In this case, it's 2 pi over 2.
In this case, b is 2. So 2 pi over 2. And that gives me a period of what? Yep.
Pi.
Pi. So this first term is going to cycle every pi. But it's not just this term. It's complicated by this one. What's the period of regular cosine? No number in front of b, no. Yep.
2 pi.
Yep, it's just going to be 2 pi. All right, we've already seen this a few times, so the least common multiple is 2 pi. So you can use the same window on this problem as you did on the last one. So least common multiple gives you your window, and it tells you what to put on the end of each answer. All right, so remember what sine cubed means. Sine cubed means this. It means to take and cube whatever your sine function is. In our case, we're not just going to have an x here, we're going to have a 2x. All right, how are we going to type all this in? Let's see. So we're going to do 3 times sine of x cubed. You want to make sure that when you type it in, that this power of 3 is not being applied to that number. We don't want to cube the 3 and get 27. The only thing being cubed is the sine 2x. If they wanted to cube the 3, then they would have had to put parentheses around the whole thing and put a 3 way outside. So that is how you type that in. Just don't forget your 2 in front of the x. Okay, so now that's correct. Yeah, the last part, there really is no extra parentheses you need. The calculator is going to put in exactly what you need. Yeah.
What button did you press to be able to just insert the 2 instead of getting rid of everything?
Oh, so you have to go to where you want to, like let's say I want to put a 4 in front of that. You have to go to where you want to put it and press second insert. And now I can put in a number in front of it.
Oh, okay.
And it'll keep letting me put numbers in front of it until I move my cursor. And now it's blinking solid again. So now if I start typing numbers, it's no longer going to insert, but it's going to overwrite what is there.
Okay.
Okay, so let's graph it and see what we get. Goes off the screen a little bit. I'm not that concerned about it because we're not looking for maximums or minimums. There's a lot of them here. But we're looking for it crosses the x-axis. Okay, how many answers do we get for that one? Yeah.
There are 6.
6. Yeah, there are 6 answers. So the longest part of this is calculating all those zeros. I already have them, so let's just write them down. We get 0.50. We're going to get 1.25. We're going to get 1.57. 1.89. 2.65. And 4.71. And what do we have to put on the end of each one of them? Yeah.
Was it 2 pi?
Yeah, the least common multiple was 2 pi. So each one of these gets a 2 pi in. Remember, don't forget what n means. Don't just start writing it and kind of forget what you're even doing. The n represents the number of cycles later or earlier you want the answer. So it can be any integer. 5, 6, 10, -8 would be 8 cycles before. But you can't be a decimal. You either look for the answer in cycle 3 or cycle 4. There's no such thing as cycle 3.6. 3, 4. So those are all the your answers. Not typical to have a problem with that many, generally, especially for a test. Because if you can calculate 2 or 3 answers, I'm sure you could calculate 6. Just more repetition. Any question on typing that all in on the calculator? Okay. So the last thing we'll finish up with, which uses pretty much like 90% of what we just did, is solving inequalities. But remember, when you solve an inequality, the answer isn't x equals something. The answer is usually like an interval. So if you had a trig function that looked like this, and I asked you, not where that function equals 0, but where is it less than 0? That means I'm looking for all of this. That red section is where my trig function is below 0. So you'd still have to find this intersect, and still have to find this intersect, but then your answer would be an interval between this number and that number. It's below 0. And that interval would repeat every cycle. So when we start solving inequalities, just keep that in mind. Your answer is going to look more like an interval. Whether it's brackets or parentheses, well, it depends on whether the problem is a less than or a less than or equal to. Can you equal the number or not equal the number? So to solve an inequality problem, you're still going to find the solutions just like it was equal to 0 instead of less than 0 or greater than 0. But then we have to take into account the inequality. We're going to be looking for one of 2 things all of the time. Where is it below 0? Or where is it above 0? That starts with finding where it exactly is 0. Answers are intervals. I already said that. And keep in mind vertical asymptotes. Because if you have a vertical asymptote in your problem, that will break your interval. You can't have an interval pass through a vertical asymptote because that would be undefined. So if you see a vertical asymptote, that's going to break your interval, and then you can start it again after it. But you need to break your interval at the asymptote. Vertical asymptotes can be a little tricky to find. The problems that I give you, they're going to be very easy. You're going to be able to look at the screen and tell where it is. So what do I mean by that? It's probably going to be like at pi, or maybe it'll be at 0, or 2 pi. You're not going to have vertical asymptotes at weird numbers that are hard to figure out. All right, let's take a look. All right, so solve, and then it says find all solutions. Okay, what do we usually like to have on one side when we're solving? Yep, 0. So let's move everything to the left. So I'll subtract the cotangent. And when we graph this, we are looking for where we are going to be under the x-axis. Now, cotangent is a function I don't have a button for. So I'm going to have to think about how to type that in. And the other thing I have to think about is the period. What's the period for sine? Yep.
2 pi.
Yep. And b is just 1. What's the period for cotangent? Yep.
Pi.
Pi. And the least common multiple, well, 2 pi. I'm not saying it's going to be 2 pi every time, but that one seems to come up a lot. Okay, let's put that in. So we've got sine of x minus, how do I put in cotangent? I don't have a button for that.
1 divided by 5 by tangent.
Yep, 1 divided by tangent. And is that all I need? Yep, sine minus cotangent. Make sure your window is 0 to 2 pi. Basically been that the entire class. And let's hit graph. So we're looking for where it is below the x-axis. Now, what do you notice that this problem has that sine and cosine don't have? Yep. It has a vertical asymptote. Where is the vertical asymptote? Looks like it's right there. Well, remember what we just set our window to. 0 to 2 pi. So where does it look like the vertical asymptote is at? Yeah. Well, remember, this edge of this window is 6.28. So these tick marks don't go by ones. Yeah? Hi. It's right in the middle. So I told you I'd make the asymptote pretty easy to find. That's what I mean by making it relatively a nice number. So let's think about where we're below 0. If you want to write where this graph is below 0, how many sections do you have to describe? Can you do it all in one? Do you need 2? Do you need 3? How many do you need? Yeah?
2.
You need 2. And it has to be under 0. It cannot equal 0. So I would say you need to describe this section. And remember, that just keeps going down. So does that. That just keeps going down. You have to describe that section. Section 1, section 2. So you need to tell me where section 1 starts and stops, and where section 2 starts and stops. Okay, where does section 1 start? It's going to get really close to this number, but I don't think it's ever going to reach this number, yeah?
0.
Right. It starts at 0. It never reaches 0 because there's another asymptote right there. There's also another asymptote right here. That's not going to affect our problem because we don't have to go that far. We're stopping before we get to it. So section 1 starts at 0. Where does it stop? I don't know. I'm going to have to find that. But once I find it, can I equal that? Or do I have to be less than that? Yeah. I have to be less than. So I'm going to need a parenthesis. So I need to find that. Or, now I need to describe the second interval. Where does interval 2 start? Yeah? Will it reach pi or just get close to it?
Just get close.
It'll just get close to it. And I don't know where interval 2 stops. I need to find that. But can I equal where it stops? Or do I have to be less than? Yeah. I have to be less than. So I still need to find 2 numbers here. But that's basically what my final answer is going to look like. And remember, those are the 2 intervals in the first cycle. You could take those 2 intervals and shift them 1 cycle later and figure out the answer in the second cycle. So what I'm going to do for that is just put plus 2 pi n on this entire interval and plus 2 pi n on that one. If you really wanted to write it formally, you should put plus 2 pi n here, 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 and here, because you can shift all of that to a later cycle or an earlier cycle. So that's a little less formal the way I did it, but it's fine for us. Just don't tell me. Okay, let's figure out these points. All right. So second calc 0. I'm figuring out where interval 1 stops. So it stops when I get to 0.90. And then I need to figure out where interval 2 stops. Okay. That's 6.28. I don't know, a little bit before it. It's probably about 5.5 maybe. I'm just estimating it. That one. It's about 5.38. Stops at 5.38. And that's how you rate your answer. Any question on that? Yeah.
So on the test, when you ask us a question like this, you want us to write the plus, the period m inside the coordinates, like how you were talking about.
You could put it like that. That's fine. Yeah, that's okay. And it would be right either way. The way you said it better, because you can take every one of these numbers and shift them all one cycle earlier, and you'll get the same type of answer again. So you do have to put something with a plus 2 pi n because it said the word all. So you got to do something. Okay. Let me just double check that. Okay. Now might be on a couple of them, but I see it on 29 and I see it on 30. These do not say to find all solutions. They only say to find the answers from 0 to 2 pi, which means you set your window from 0 to 2 pi. You write down every number you can see in the window and you stop. You do not have to put plus 2 pi n because the directions don't say all. So that's actually a little easier than what we did. Okay, so reminder, I'll be up to school tomorrow if anybody needs to come for anything, make up a test. Progress reports also close on Friday.